In this short video, we just wanted to share a few ideas about the derivative, which is an important idea from calculus, and slope, which is a very important idea from algebra and secondary school mathematics. So informally speaking, the derivative is a measure of the varying relationship between two quantities. So we might have an original function which captures the direct relationship between two quantities, and then the derivative gives us a way to think about and to measure that original function. It can tell us about how the relationship varies. Informally speaking, the derivative at a point is the slope of the tangent line at that point. And because we're talking about a tangent line, the derivative therefore provides us information about the best linear approximation of the function near that given point. Now that's derivative at a point. There's also derivative function, but usually we will kind of use the term derivative, and sometimes we can kind of gloss over that, but really we should distinguish these: derivative at a point and then the derivative function. The derivative function is a function whose inputs are the points, of the independent variable, but the outputs are the derivative values at each of those specific points. Another informal way to think about derivative is as the instantaneous rate of change in the dependent variable relative to the independent variable. So this notion of rate of change gives us another connection to slope and rate of change from secondary school mathematics and algebra. So one of those connections that we wanted to draw here is between just the notation that's used for derivative. So let's start with the slope formula. So we have the familiar slope formula. We have the changes in the dependent variable as compared to the change in the independent variable. And a lot of times this would be written delta y over delta x. And in that case, what we're dealing with there is a finite change in y and a finite change in x. Now with derivatives, we have this common Leibniz notation of dy dx. And this dy and dx is representing an infinitesimal change in the dependent variable divided by an infinitesimal change in the independent variable. But notice it's still keeping that familiar shape and idea of slope. Formally, we can develop a definition of the derivative of a real-valued function f by using this notion of instantaneous rate of change. And what we'll actually do conceptually is start with average rate of change. And we're going to look at average rate of change over this neighborhood of h. And so let's look at the derivative of f at the point A and looking in this neighborhood of h. So what we would have then for an average rate of change is in the numerator f of a plus h minus f of a, so that's the differences in the dependent variable, divided by a plus h minus a. And so in the denominator what we have is the differences in the independent variable. So structurally you can see this as the change in y over the change in x, or exactly what you would expect for a rate of change or slope. Now I said average rate of change because what this actually does is it just takes from a to a plus h, and over that little neighborhood it's just getting the average rate of change. What we want to do is move that towards an instantaneous rate of change. So to get to the instantaneous, what we will do is shrink the neighborhood, or we will make h tend towards 0. And as h tends towards 0, what we're actually doing formally is we are taking the limit as h approaches 0. Assuming that the limit exists, this gives us our definition of derivative at that point A. Here we have a picture of how you can conceptualize this using secant lines. The secant lines have a slope, and that slope is the average rate of change between a and a plus h. And as we take the limit of h going to 0, we end up with the instantaneous rate of change. So just to reiterate, the main idea that we wanted to share in this short video is that the definition of derivative is not some set of symbols that you should memorize or that you should have students memorize. It's really something that you should see structurally as having the same structure as slope. Definition of slope being rise over run, or the change in the dependent variable over the change in the independent variable. So how are those two things varying? How sensitive are the changes in y to the changes in x? That's what you want to see structurally, and when you see slope that way, you also want to see the definition of derivative that way. And even before students get to calculus, they're capable of thinking about the rates of change on nonlinear functions. So like they could have some fancy curve nonlinear relationship. They can still spot these points where there's a 0 slope instantaneously at that one point. They can also compare, very large positive slopes or very small slopes or very large negative slopes. They can still qualitatively reason about the changing slopes or the changing instantaneous rates of change, even if they can't formalize that or compute it in terms of calculus. And also having students think about slope and rates of change for nonlinear functions can give them an appreciation for linear functions, where they can actually realize, oh, linear functions are these functions where the rate of change is independent of the point A. It doesn't matter where you are, it's the same slope or the same rate of change everywhere. One final note here, just because we've seen two other fundamental theorems, the fundamental theorem of arithmetic and the fundamental theorem of algebra, we thought we'd throw in the fundamental theorem of calculus. So this theorem has several different components, and you can phrase it in different ways, but in a nutshell, the fundamental theorem of calculus says that antidifferentiation and integration are basically the same thing. So antidifferentiation is working backward or going kind of in the inverse direction from derivatives. So you work backward from the derivative function to find some other function that has the given derivative. Integration is this process of finding accumulations or finding the area under curves. So it's not obvious that these two would be the same thing, but the fundamental theorem actually tells us that they are the same thing, essentially. Now, we can think of this analogously to, for instance, multiplication and division. So you're probably so comfortable and familiar with multiplication and division that it seems very clear that those are inverse operations of one another. And in fact, you can just define division as the inverse operation of multiplication. But you don't have to define it that way. You don't have to define it in a way where it's just obviously the inverse of multiplication. For example, you can define division between two numbers x and y. You can say division is what you get when you take x things and put them into y different groups. The outcome of the operation is the number of things in each of those groups. So that's just a definition of division on its own merits, but it turns out to be the inverse of what you get when you define multiplication on its own merits. So in the same way, anti-differentiation is kind of the inverse of derivatives or differentiation. But integration can be thought of just on its own merits as this accumulation or area under curves. Turns out they're the same thing, basically.